So welcome back. We have been discussing on the cyclization of pentoses and hexoses. So we saw the example of D-glucose, how cyclization happens, and what is the reaction based upon which the cyclization is happening. Okay. We were discussing that the D-glucose, that is aldose, when it actually cyclizes, it forms a pyran structure, and hence we usually call it as a pyranose. Okay, aldohexose, specifically glucose, when it gets cyclized, what happens? It takes up a pyran structure, and hence it is D-glucopyranose. Depending upon the positioning of hydroxyl group with respect to the anomeric carbon, which is anomeric carbon C1. Okay, anomeric carbon, we can have two isomers, that is alpha isomer and beta isomer. Beta isomer, when the hydroxyl group is, you can see here, hydroxyl group, when it extends above the plane, it forms the beta glucopyranose, and when it is below the plane, it is the alpha glucopyranose. Now we need to see how the furanose structure is formed. Okay, the ketose, the ketohexose, that is the fructose for an example, it forms a furanose structure, because every time we saw that the cyclization happens when the carbonyl carbon reacts with the hydroxyl group, isn't it? And where is the carbonyl carbon present in the case of the fructose? It is in the second position. Okay, I hope this is clear. So this is a D-fructose, the structure of D-fructose, the linear chain. And you can see the first carbon, it is in the form of CH2OH, while it is the second carbon which is in carbonyl form, right? And it is this what you call carbonyl carbon, which here, okay, this reacts with the hydroxyl. Carbonyl compound, it reacts with the alcohol of the C5. So there is a reaction between the CO and the COH. Okay, and you can see always the bending happens in this way. So there is the first carbon CH2OH, the second the carbonyl carbon, and likewise the fifth carbon CHOH, right? Fifth one CHOH, and then sixth CH2OH. Leaving behind the CH2OH outside the plane starts with the second carbon. Okay, and likewise it goes, while again sixth carbon is left out, while the plane or the chain is completed with the oxygen of the hydroxyl group. Now what happens? This is the hydrogen, isn't it? And this is actually pair of electrons, right? This will shift to or gets transferred to the oxygen on the carbonyl molecule. Okay, so what happens when this gets shifted onto the oxygen? This will turn into hydroxyl. Okay, it gets reduced, so it becomes COH. Yeah, it becomes COH. Okay, and sorry, there is a bond formed between this oxygen and carbon. So what is the resultant product? It will be this way. Okay, CH2OH, and the sixth CH2OH is left behind. So what is the number of what you call carbon in the chain? Only 4. Okay, and the fifth position is occupied by oxygen. And such a structure with carbon chain with the oxygen in the ring, it is known as a furan. Okay, and here what happens? The furan is formed from fructose, so it is D-fructofuranose. And in D-fructofuranose, depends upon two isomers is possible depending upon the position of hydroxyl group on the anomeric carbon. Which is the anomeric carbon? Here it is the second carbon. In the D-glucose, it was the first carbon which was anomeric, but in ketose, the fructose, it is the second carbon which is anomeric. Okay, depending upon the position of the hydroxyl group on the second carbon, that which is the anomeric carbon, we can have two isomers. When hydroxyl group is above the plane, we call it as beta D-fructofuranose. While it is below the plane, we call it as alpha D-fructofuranose. Okay, this is a cyclization process which happens in the ketose in fructose. Okay, I hope it is clear. Next is mutarotation. We have already seen that glucose or fructose, etc., they can exist in two forms. One is the linear open chain, and the second is the cyclized form, alpha or beta anomers. So that when the glucose is dissolved or it forms an aqueous solution, when we add glucose in aqueous solution, what happens is, in the aqueous solution, the glucose can exist in three forms. That is, it can exist in linear form or the open chain form. It can also exist in alpha or beta cyclized form, okay, ring form. So it can there can be alpha D-glucose, beta D-glucose coexisting with open chain, but obviously the proportion will be different. That is, the amount will be different. Okay, there will be only a very small amount of the open chain glucose, while there will be plenty of beta D-glucose. Okay, so that kind of a interconversion, okay, that is known as a mutarotation. So that is when in aqueous solution the D-glucose can get converted from alpha to beta, beta to chain, chain to, so that kind of interconversion is known as mutarotation. Okay, so the process of interconversion of alpha and beta anomers of D-glucose in aqueous solution, in which one ring form opens briefly into linear form, then closes again to produce another anomer. I hope it is okay. So alpha anomer may may form an open chain, and this then get converted into beta form. So such kind of interconversion is what is known as mutarotation. Okay, so there's a solution of beta D-glucose and a solution of alpha D-glucose eventually form identical equilibrium mixtures having identical optical properties. If we have taken specifically beta D-glucose and we have made a solution of it, we can, after some time, we can see that it will contain alpha D-glucose, beta D-glucose as well as linear chain. Okay, but this mixture will contain 1/3 of alpha D-glucose, 2/3 of beta D-glucose, and very small amount of linear chain. So that is what happens. Okay, so we saw the different kinds of isomers so far, and what were that? We saw the stereoisomers, and stereoisomers are where the atoms, here it refers to the constant groups, okay, are connected in the same order but differs in spatial arrangement. Okay, so that is what happens. That is what the stereoisomers. Stereoisomers can be of two types. Right? What are they? The enantiomers and diastereomers. Okay, enantiomers where they are non-superimposable mirror images. They are mirror images. Okay, the two stereoisomers which are mirror images, we can call them as enantiomers. What is diastereomers? They are not mirror images. Okay, we have plenty of examples. D-glucose, D-galactose was one example of diastereoisomer. Okay, now here what happens? The epimers. Okay, diastereomers can be divided into epimers and anomers, right? Epimers where the pair of isomers, they differ only with respect to the constant groups around a particular carbon atom. Okay, this is D-mannose and D-glucose. At which position they are epimer? They are epimer 2 with respect to the carbon 2. Okay, another set of examples is D-glucose and D-galactose. They were epimers with respect to the carbon 4. Right. Then anomers. This happens when it is in ring form or closed form. Okay, they are isomers that differ at a new asymmetric carbon atom, which is a new asymmetric carbon. That is what is referred as the anomeric carbon. And in the case of glucose, it is the first carbon. Okay, so with respect to first carbon, the position of hydroxyl determines which is alpha, which is beta. So that is anomers. Okay, so these are the different configurational isomers. Okay. Now we will pass on to the next one. Yeah, this is just structural models of glucose, which shows the alpha D-glucose formation. Next is glycosidic linkage. This is one of the most important reactions which happens between two glucose molecules. Glycosidic. Whenever a carbohydrate like take part in a bonding formation with any other molecule, we call that bond as a glycosidic bond. I hope it is clear. Whenever, so here you can see one example. So this is, what is this? It is a ring structure, right? How many carbons are there? 6 carbons, so it is hexose, right? It is a hexose. And then this is a third carbon is having, so always we start numbering like this: 1, 2, 3, 4, 5, and 6, isn't it? With third carbon, hydroxyl is on the upper side of the plane. So it is a D-glucose, right? What happened to D-glucose? Actually, here it should be H and OH below. That is beta, like alpha D-glucose, right? And what happened to alpha D-glucose over here? OH, it has got methylated. It's methylated at this position, right? So it had formed a bond over here. Okay, OH is removed and instead OCH3 has come into being, right? So this bond, there is a monosaccharide. This is a monosaccharide has formed a bond with like oxymethyl. So this bond is referred as a glycosidic bond. Okay. this is ribose sugar. Okay, ribose sugar. So this ribose sugar 1, 2, 3, 4 and 5 CH2OH, right? So here what has happened? This has formed a bond with the nitrogenous base, fine. So this is another bond. This is again a glycosidic bond. I hope it is clear. So whenever monosaccharide forms a bond with another molecule, it is known as a glycosidic bond. Usually it is known as a glycosidic bond. Okay, and this bond, it can be of two types. You can see O-glycosidic bond and N-glycosidic bond. Okay, what is the difference here? So here what has happened is, in the case of O-glycosidic bond, the bond, it is through oxygen. Fine, it is through oxygen, the glycosidic bond is happening. What about here? It is through nitrogen. Okay, the glycosidic bond happens through the nitrogen. Okay, so that is why it is known as a N-glycosidic linkage. Okay, so whatever it is, the glycosidic linkage is a bond formed between the anomeric carbon atom of a carbohydrate and oxygen or any other molecule. Okay, actually that is it. It's known as a glycosidic bond. When we are speaking about carbohydrates alone, this kind of a glycosidic bond, that is the O-glycosidic bond, is more important. And this definition actually represents the O-glycosidic bond, where the anomeric carbon atom, it forms a bond with the oxygen atom of an alcohol. Okay, this is referred as a glycosidic bond. And glycosidic bond plays a very important role in the formation of oligosaccharides and polysaccharides. So now we will be continuing with the O-glycosidic bond alone. But when we come to nucleic acids, when we describe the structure, we will come back to the N-glycosidic bond. Okay. So here, whenever we are speaking about the glycosidic bonds under carbohydrates, what we are mentioning, it is specifically the O-glycosidic bond. Okay. So O-glycosidic bonds are prominent when carbohydrates are linked together to form long polymers. When two monomers come together and bond with each other, the bond is glycosidic bond, specifically the O-glycosidic bond. Okay. Now we can see how it is formed. Okay. So this is a O-glycosidic bond. Right. Let me see. Yeah. So this is D-glucose. What kind of D-glucose it is? Right. It is alpha D-glucose. Why is it so? Because hydroxyl group, it projects below the plane. Okay. And this is also D-glucose, but it is beta D-glucose. Why? Because here the hydroxyl group is extended above the plane. Hydroxyl group attached to the anomeric carbon specifically. Okay. Now these two molecules of D-glucose, it is going to form a glycosidic bond between them. What happens is, it is actually a condensation product. Okay, it is a condensation product. So there is a removal of water. Okay, so how is it released? HO and H. Okay, it could be H and OH, whatever it is. So from here, this OH and this OH, a water molecule is released. So what happens? What is left over? Oxygen is left over, and a bond is formed like this. Okay, you can see water is removed and the bond is formed in this way. So it is through oxygen the two monosaccharides have got bonded. Okay, so this is glycosidic bond. Fine. Now we have to name the bond, because naming the bond is also important. Okay, even the new molecule formed is a disaccharide. Okay, disaccharide is a oligosaccharide with two monosaccharide units, isn't it? So these two, so you can see condensation, that is removal of water, results in the formation of disaccharide. Okay, and this disaccharide, which is formed of two glucose molecules, they are known as maltose. Okay, maltose, when it breaks down, it releases. So when water is added to this disaccharide, what happens? You can see when water is added, what will happen? It will give rise to two glucose molecules. Okay, now coming over here to maltose. How do we name it? The first thing is, we write the bond based on which carbon atoms have come into play for the bond formation. Here it is first carbon, C1 of the first monosaccharide, okay, C1, and C4 of the second monosaccharide. So it is 1 to 4 bonding. Okay, it is 1 to 4 bonding. Now, what kind of monosaccharide it is? The first one, it is alpha D glucopyranose, right? So when it is bonded to form a disaccharide, we call it as alpha D glucopyranose. 1 to 4, this is D-glucopyranose. So it is D-glucopyranose. I hope it is clear. Okay. Now, when we say what kind of bond it is, you needn't write the whole thing. Instead, you can very simply write it is alpha, because the first sugar is alpha type. 1 to 4 bonding. So it is alpha 1 to 4 glycosidic linkage. Okay, that is how we name it. So this is alpha 1,4 glycosidic linkage. I hope it is clear.